Hello students, I am Dr. Geetu Gambhir. Today, I bring you the next learning episode in BSc Forensic Science on behalf of the content writer Dr. Vimal Rar and Ms. Deepika Bhandari on an important unit of the paper Technological Methods in Forensic Sciences, that is paper chromatography and classical column chromatography. Today, in this lecture, you will be learning about paper chromatography, its types and applications. You will also be acquainted with the classical column chromatography, principle of elution and classification of column chromatography. In this lecture, you will also get to know about the process of elution, the chromatogram and the measures of column efficiency. Applications of paper chromatography. Paper chromatography has been used for separation of mixtures having polar and non-polar compounds such as amino acids, hormones, drugs and other biochemicals. It has been used for the evaluation of inorganic compounds. Although paper chromatography has become very popular due to its simplicity, it suffers from various limitations such as long development time, poor separation, low accuracy in quantitative determinations and low reproducibility. Introduction to classical column chromatography. Classical column chromatography or column chromatography is one of the most useful techniques for the separation and purification of liquids as well as solids. In this type, the stationary phase is chosen as solid, whereas the mobile phase is chosen as a liquid, and hence it is a solid liquid technique. This technique is based on the principle of differential adsorption of the substance by the adsorbent. The choice of a solvent depends on the nature of the solvent as well as the adsorbent, and usually the adsorbents which are employed for this technique comprises of silica, alumina, calcium carbonate, calcium phosphate, etc. The rate at which the components separate depends on the activity of the adsorbent and polarity of the solvent. The separation tends to be slow when the polarity of the solvent is very low and activity of the adsorbent is very high, but it results in good separation. In case the polarity of the solvent is very high and the activity of the adsorbent is low, the separation tends to be rapid but results in pure separation. The adsorbent is mixed with a suitable liquid so as to form a slurry and placed inside a cylindrical tube which is plugged at the bottom with a piece of glass wool or a porous disc. The sample is to be separated, is dissolved in a suitable solvent and introduced from the top of the column and allowed to pass through it. As the sample moves through the column, separation of the components take place depending upon the ability of adsorption. The different fractions are collected separately. Distillation or evaporation of the solvents from the different fraction gives the pure components. Principle of elution. Column chromatography separation involves the stationary phase being held in a narrow tube or a column. The mobile phase or eluent along with the mixture of components, which is the solute, is forced through the tube having the stationary phase under pressure. This process is termed as elution. Eluate is a fluid emerging from the end of the column. The columns are either packed or open tubular Packed column is filled with small particles of stationary phase, whereas the open tubular column is usually a narrow capillary tube with the stationary phase coated inside the wall. Classification of column chromatography. Following table classifies the various types of chromatographic techniques based on the type of mobile phase used: liquid, gas or supercritical fluids. Supercritical fluid mobile phase method is relatively new and is gaining popularity. Liquid chromatography can be further divided into 5 categories depending upon the stationary phase used and the mechanism of redistribution followed to attain the equilibrium. Components of the mixture follow different mechanisms of interaction or redistribution, namely adsorption, partition, ion exchange or size exclusions. Likewise, a gas chromatography can be further subdivided into 3 types. It is to be noted that liquid chromatography can be carried out in column as well as planar surface, but gas chromatography and supercritical chromatography can only be performed in column. General classification of the liquid chromatography, wherein the mobile phase is a liquid. It involves liquid-liquid partition, liquid adsorbed on a solid and partition between the immiscible liquids. In case of the liquid bonded phase, the organic species is bounded to the solid surface and the partition between the liquid and the bonded surface takes place. In liquid solid or adsorption chromatography, the stationary phase is a solid and adsorption takes place on the solute on the stationary phase. In the ion exchange chromatography, ion exchange resin acts like a stationary phase and ion exchange takes place between the solute and the stationary phase. In the size exclusion type of chromatography, the liquids in the interstices of the polymeric solid acts like a stationary phase and partition or sieving of the solute takes place between the stationary phase and the solute. In the gas chromatography, the mobile phase is a gas. In the gas liquid chromatography, the liquid adsorbed on a solid acts like a stationary phase and the partition between the gas and the liquid takes place by the solute. The gas bounded phase chromatography involves the organic species bounded to the solid surface as a stationary phase and the partition between the liquid and the bonded surface takes place by the solute molecules. In the gas solid chromatography, the solid phase is the stationary phase and it involves the adsorption of the solute on the solid phase. In the superficial fluid chromatography, the mobile phase is a superficial fluid. The organic species bonded to the solid surface acts like a stationary phase and the partition between the supercritical fluid and the bonded surface takes place by the solute particles. Process of elution. The process of elution and separation of various components by column chromatography can be depicted by the following diagram. It can be seen in the figure which showing the process of elution and separation of various components by column chromatography. As can be seen, a solution having components A and B in the mobile phase is introduced at the head of the column. The elution process begins when the addition of fresh solvent, that is the mobile phase or the eluent, which is applied to the top of the column takes place. The mixture of A and B is washed down into the column and these components distribute themselves between the two mobile phase and the stationary phase. The average time spent by a particular component in either the stationary phase or the mobile phase depends upon its affinity for that phase. In the diagram, the component B is retained on the stationary phase for a longer period than the component A. These differences in their rates of movements, A moving faster than the B along the length of the column, causes the components of the mixture to separate into bands or zones. Complete isolation of the separated components is achieved by passing sufficient mobile phase through the column and collecting them at different times. At times T3 and T4 as represented in the given figure. The chromatogram various solutes emerging from the column are observed with the detectors. The detectors may be specific for a type of a solute detected. A chromatogram is a graph showing the detector response plotted against the elution time. In the figure 2, a chromatogram of two components, such a plot is useful for carrying out both the qualitative and the quantitative analysis. The position of the peak at the time axis are used for the qualitative analysis, whereas the peak areas reveal the quantitative aspect of the components. In the figure 2, chromatogram depicting the detector response against the elution time. Let us understand certain terms used in the column chromatography. Retention time. Retention time is the time taken by the solute to reach the detector after the mixture is injected onto the column. It is represented by TR. Adjusted retention time. T dash R is given by the expression T dash R is equal to TR minus TM, where Tm is the time taken by the unretained species or the mobile phase to reach the detector. It is also referred to as the dead time. So, the adjusted retention time for a solute is to move through the column beyond the time required by the mobile phase to travel through the length of the column. The partition coefficient, the solute components partition themselves in the mobile phase and the stationary phase as they move through the column. If the column is run slow enough, the concentration of the solute in the stationary phase and mobile phase reaches the equilibrium. The equilibrium constant or partition coefficient K for this reaction is defined as Cs upon Cm, where Cs is the molar concentration of the solute in the stationary phase and Cm is the molar concentration of the solute in the mobile phase. Most of the chromatographic separations are performed under the linear conditions, that is, Cs is directly proportional to Cm. Thus, for the solute X, it may be written as X in the mobile phase and X in the stationary phase. Capacity factor. It is also called retention factor and is used to describe the rate of migration of the solute on the column. The capacity factor K dash is defined as K dash is TR minus Tm upon Tm. This equation implies that longer a solute is retained by the column, greater is the capacity factor. If this factor is in the range of 20 to 30, elution times becomes too long, but if it is less than 1, the solute passes out without interacting with the stationary phase. The ideal value lies between 1 to 5. selectivity factor or relative relation alpha. This term describes the extent of separation between two components. Greater the value of selectivity factor or relative retention alpha, greater is the separation between the closely spaced components in the chromatogram. It is expressed as alpha is equal to K dash B upon K dash A, where K dash B is the capacity factor for a more strongly retained solute B and K dash A is the capacity factor for the solute A, which is eluted faster. It can be rearranged to give Tr for the component B minus Tm divided by Tr of the component A minus Tm. Both capacity factor and selectivity factor can be easily calculated from the chromatogram and are used to monitor the performance of the column. Measures of the column efficiency. Column efficiency depends upon how well the column is able to separate the components of the sample. Two factors contribute to this aspect: width of the peak and difference in the retention time between the peaks. Wide peaks result in poor separation, and the peaks having very close retention times may not be able to resolve it completely. We will deal with the peak width before elaborating upon the resolution of the peaks. Effect of the peak width. The width of the chromatographic peak as is recorded on the chromatogram is the culmination of various phenomena taking place in the column. So, we will elaborate on theoretical terms related to rate of movement of a solute down a column. Efficiency of separation can be attributed to the concept of height equivalent to theoretical plates, which is also called as HETP or simply plate height. A theoretical plate is an imaginary concept that does not conform to any actual parameter in the column, but for evaluation purposes it is a useful measure. Plate height refers to the length in the column within any two adjacent plates. The name is derived from the theory of distillation, in which column is made up of series of bubble cap tiles, plates, and separation is performed in these discrete stages or plates. Plate height is the length that is able to achieve equilibrium of the solute between the stationary phase and the mobile phase under the particular set of conditions of flow rate, temperature of column, type of stationary phase, etc. The solute then moves up down the column with equilibrated mobile phase in the stepwise manner from one plate to the next. The concept of theoretical plates in chromatographic column was given by A.J.P. Martin and R.L.M. Signage, for which they were awarded the Nobel Prize in Chemistry in 1952. Figure 3 represents a separating column for separation of various components. The efficiency of the column to separate components is dependent upon plate height. A column of a particular length with lesser plate height and thus more number of theoretical plates is more efficient than the one with lesser number of theoretical plates. For a solute passing through the column of length L in centimeters, having n number of plates and h plate height in centimeters, correlation between them is given by the expression n is equal to L upon h. Difference between the plate heights of the various solutes arises due to difference in their partition coefficients. Plate height can vary between 0.1 to 1 millimeter in gas chromatography and approximately 10 micrometers in high performance liquid chromatography. Plate numbers can range from few hundred to several lakhs. Figure 4 shows an elution peak and various parameters for the calculation of N. A figure 4 is a typical chromatogram showing retention time, peak height and bandwidth for estimating the number of theoretical plates, where it can be seen that W is the peak width or the bandwidth, W half is the bandwidth at half the height of the peak. We can assess the efficiency of the column from the chromatogram by visualizing the shape of the peaks. Smaller plate height translates into a symmetrical narrow Gaussian shaped chromatographic peaks, and reverse is true for the peaks with greater peak width. To calculate N from the chromatogram, following expression is used. N is equal to 16 TR upon W square. Here TR and W are the time measurements in the same unit. Length of the column L should be known to obtain the plate height H. Another method for obtaining N, which some researchers prefer, is by using the peak width at half the height. Number of the plates is then given by N is equal to 5.54 into T upon TR upon W square. The results obtained in both the cases are comparable. Since past 50 years, researchers have been developing meaningful relationships describing the effects of experimental parameters for reducing the plate height on various columns. As solute moves through the length of the column, band broadening is observed, which is reflected as a broad peak on the chromatogram. This phenomena is inevitable. So, conditions have to be reached upon where it occurs slower than the band separation. Several physical and chemical factors decide the rate of band separation and band broadening, and these are discussed in the chapters on gas chromatography and high performance liquid chromatography. Effect of retention times, which is also called as resolution. The resolution is a measure of low well two adjacent peaks is separated by a column. Baseline separation should be achieved for the complete resolution. Figure 5 illustrates the performance of 3 columns with different resolving powers for 2 components A and B. The solution is defined as R is equal to 2 delta Z upon WA plus WB, which is also equal to retention time for the component B minus retention time for the component A upon WA plus WB, where the terms on the right side of the equation are as illustrated in the figure. Figure 5 showing the performance of 3 columns with different resolving power for 2 components A and B. As is clear from the figure above, the resolution of 0.75 results in incomplete separation. At the resolution of 1.0, there is 4% overlap of peaks. Complete resolution is obtained at the values above 1.5. The resolution for any given stationary phase can be improved by using a longer column. This increases the number of plates, although it also increases the time required for elution. A compromise is generally made between the time taken and resolution. It has been observed that resolution is proportional to Vn. It has been observed that resolution is proportional to square root n. Therefore, doubling the column length increases the resolution by square root 2. It is, however, more effective to vary the capacity factor K dash or selectivity factor alpha by varying the mobile phase for the liquid chromatography and stationary phase for the gas chromatography. Applications of column chromatography. Column chromatography has wide range of applications. Few of them are separation of mixture of compounds, purification process, isolation of active constituents, estimation of drugs in formulation. Conclusion. Chromatographic techniques are invaluable tools of analysis as the components of mixture are first separated, thereby facilitating the analysis of the complex mixtures. They are useful analytical technique in the field of forensics. Various types of chromatographic techniques are present for the analysis of different compounds. With all these information, here we come to the end of today's lecture. Do keep in mind what we discussed today. We will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQ quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.